Hello everyone, this is Dr. Rajesh and I am again with you with a new video lecture on the topic subgroups, and in this lecture we will be covering an important result concerning the subgroups. So that result is given by arbitrary intersection of subgroups. What is the meaning of arbitrary? That is intersection of any family of subgroups of a group is a subgroup. Like in the last lecture, we have studied that intersection of only two subgroup was also a subgroup. Okay, but in this case here will be large number, arbitrary number. It will be h1, h2, h3, h4 intersection and so on. It will continue. There are many subgroups, arbitrary, infinitely many subgroups. So what will happen in that particular case? So I am again writing that let, and what I'll name, I'm going to prepare, this is called collection of subgroups. Let h1, h3 and so on. So on means it has many elements. B collection of subgroups of G, that is, and in compact form I am representing it as h lambda, where lambda belongs to this. This is called lambda and this is called capital lambda, and here it is indexing set to index the sets. Like indexing set means 1 2 3, that kind of set is called indexing set. It is called indexing set. So that is, this symbol is for used for, that is, B collection of subgroups of G. So this is collection of subgroups of G. We know that H1, H2, H1, H2, H3 and so on, or H lambda for each lambda belonging to indexing set is subgroup of G, is subgroup of G, and if it's subgroup, this implies that identity elements belongs to H lambda for each lambda belonging to this capital lambda indexing set. Means in each and every h1, h2, h3, in any number of subgroups it may be, in each of them there will be identity element. If it each of them will be containing identity element, may I say that their intersection h1 intersection h2 intersection h3 intersection up to so on will contain the identity element. This implies that in compact form this intersection is written as intersection h lambda, and lambda here written as belonging to indexing set. So if I say that this indexing set, that intersection of that arbitrary elements is non-empty because it contains identity element. So this is non-empty. This is non-empty. So this will be non-empty. Let this intersection of arbitrary elements is named as H. So also we know that each H lambda is subset of G, and this is for each lambda belonging to indexing set, because each H lambda is subgroup of G. If it is subgroup, therefore it will be subset. This implies that H1 is subset of G, H2 is subset of G, H3 is subset of G, and so on. This implies that H1 intersection H2 intersection H3 intersection and so on, all the subset of G. This implies that H lambda, lambda belonging to capital lambda is subset of G, and this we have assumed as H. This implies that H is subset of G, and we have already proved that H is non-empty. Next we have to prove that H, which is equal to intersection H lambda, lambda belonging to capital lambda, that is indexing set, is a subgroup G. For the same, let AB belonging to H equal to intersection H lambda, lambda belonging to capital lambda. This implies that since these two elements A and B are in the whole intersection, H1 intersection H2 intersection H3, so that will go in each and every subgroup. So this A and B will belong to H lambda for each lambda belonging to capital lambda. Since each H lambda, where lambda belonging to capital lambda, is subgroup of G, therefore AB belonging to H lambda for each lambda belonging to capital lambda implies AB inverse belongs to H lambda for each lambda belonging to capital lambda, because subgroup has this property. So this implies that if it will go in H1 for each lambda means H2 and H3, so that will also enter into their intersection. This implies that AB inverse also belongs to intersection lambda belongs to capital lambda. So by that theorem, intersection H lambda, lambda belonging to capital lambda is equal to H, is a subgroup of G. Therefore we have proved that in arbitrary intersection of subgroups is again a subgroup, and the result used to prove this theorem is again the same that we have used, and it can be given as necessary and sufficient condition for a non-empty subset H of a group G to be a subgroup is that this condition A and B two element we will assume, and we will prove that A B belongs to H. So this condition we are again and again using in proving the result. So that is all I have from this lecture. I hope you will be able to understand that arbitrary intersection of subgroups is again a subgroup. So I will be very soon with you with my next video lecture. So this is Dr. Rajesh saying goodbye. Thank you very much. Thank you for watching. Take care. Bye bye.